Hi guys, sound check.
Check.
Hi guys, I think we should start. The plan for today is to discuss polynomials in one variable, and then we will discuss the ring of reminders based on polynomial ring. Okay, so polynomials. So first of all, I want to fix a field. So let F be a field. So what's the polynomial over the field F? So a polynomial is a picture. So a picture of this form. a0 plus a1x plus and so on plus an x to the n. So here, these things like a0, a1, an are just elements of the field F. And x is just a symbol. This is just a symbol. And all these operations are just formal pictures. So this plus is just a part of the picture. This multiplication is just a part of the picture. So so a polynomial is just a picture of this form. So we do not suppose to multiply a1 by x in any way, shape, or form. It's just a formal notation. I will explain why we need this strange definition. But probably you already have the definition of the polynomials, and the polynomial were functions. But now we don't want them to be functions; we want them to be pictures. And formally, so every polynomial is uniquely determined by the coefficients given here, and the number n could be any number from 0, any natural number actually, from 0 to any positive number. Now, I want to discuss how to compare polynomials, how to add polynomials, and how to multiply them. So you probably know all of this stuff, but I just want to go through all of them. So if you have any other polynomial g, it's also a picture of this form, but probably the integer m is different here. So we will say that, oh, by the way, so here we have these numbers are called coefficients, e0, a1, an, and if a coefficient is not present in the polynomial, like an plus 1, an plus 2, and so on, we may think that they are just 0. So if I use a coefficient of a polynomial which is not here, it's automatically 0. This is our assumption, and this assumption will simplify all the formulas I will write later. But just in case you to know what's going on here. So I will say that the polynomial f equals g if and only if all the coefficients are the same. And here I assume that if k is strictly greater than n, then ak is 0, and if k is strictly greater than m, then bk is also 0. If you want to add and multiply polynomials, you use the usual formulas. So the sum of the polynomials is given by this formula, ak plus bk x to the k, and k goes through 0, from 0 to all the integers. So of course the sum is finite because for sufficiently large k, both coefficients are 0. So, and the multiplication is computed by the formula like this. I will write the formula and then I'll say it again on here. So the polynomial, so on the right hand side we have polynomial. K denotes the degree of which symbol x, and the coefficient, each coefficient is computed by this formula. So here this sum is also finite because it goes through non-negative u and v, and k is a finite number which is here, and the sum for k is also finite because for sufficiently large u and v, all these numbers will be 0. Okay, so these are the formal rules. Now, if we present our polynomial f in this form, and additionally this coefficient is non-zero, we will say that this is the leading coefficient. And in this case, we say that the degree of the polynomial is n. So the degree is just the number of the highest of the highest power that appears in our polynomial. Now, what's important, by the way, if f, so the set of all polynomials will be denoted by this. So this is just the set of all polynomials. F is a polynomial with coefficients in f, or f. So it's a straightforward computation that the set f of x with two binary operations plus and dot, which we introduced above, is the commutative ring. Just in case, the neutral element with respect to addition is the polynomial with all the coefficients being 0, which is called zero polynomial and is also denoted by 0. The neutral element with respect to multiplication is the polynomial with its 0 coefficient being equal to 1, and all the other coefficients are 0, so plus 0x plus and so on. So this is the neutral element with respect to multiplication. It will be simply denoted by 1 as well. Okay. Now, I want to clarify the reason why we want the polynomials to be pictures and not just functions. So suppose, now an example. So if we have a polynomial f, we can produce a function f hat from the field f to the field f. And the function works as follows. So if we have this polynomial, we can substitute a value. So if a is an element of f, then f hat of a equals to this expression where we substitute a instead of x. And here, all these operations are the operations inside the field f. So this is just a usual function given by the polynomial. But what is interesting here is that if the field f is very small, then different polynomials may define exactly the same functions. For example, this happens if you take Z2 to be a field. Then let's take this family of polynomials, just nth power of x. So these are distinct polynomials in this ring, just by definition, because they have different coefficients. But now, if you consider the corresponding functions from Z2 to Z2, then each of these polynomials takes 0 to 0, and it takes 1 to 1. So all these functions are the same. There is no difference between these functions. But we don't want to identify these polynomials. We still want to produce a ring where all these objects are different. So in order to produce such a ring, we have to think of the polynomials as of pictures instead of functions. On the bright side, when you deal with pictures, how do you compare pictures? You compare them coefficient-wise. You don't have to substitute elements instead of the variable and compare the result one by one for each input. Instead, you just use the coefficient-wise comparison. It's just easier to compute. So this is the reason why we want the polynomials to be pictures. Okay. Yeah. By the way, I realized that I need to say a couple of words about the degree of the polynomial. So well, if we have a polynomial, as I said, if this guy is not 0, then the degree of f is equal to n. But what if all the coefficients are 0? So I forgot to mention one specific case. So if all the coefficients are 0, which means the polynomial is 0, we define the degree of the 0 polynomial, let me write it like that, to be minus infinity. So if you have a non-zero constant term, so for example, if you have an element of the field, like lambda is an element of the field which is not 0, then lambda is considered, maybe considered as a polynomial in the variable x. Well, it's a polynomial where h0 equals lambda and all other coefficients are 0. This polynomial has degree exactly 0. So the degree of lambda is exactly 0. And if lambda is actually 0, then the degree of lambda is minus infinity. So these allow us to distinguish 0 and non-zero constant polynomials. So so if your polynomial has degree 0, it means that it's a non-zero constant from the field. In particular, this is an invertible polynomial. And you will, what is important about the degree, if you have two polynomials, here f is a field, then the degree is additive, in the sense the degree of the product is equal to the sum of the degrees. And the rule works well in case of the 0 polynomials. For example, if one of the polynomials f or g is 0, then the corresponding degree is minus infinity. In this case, we just assume that minus infinity plus anything is equal to minus infinity. So in this case, this formula works for any polynomial, so you don't have to specify that your polynomials are non-zero. So this formula works perfectly fine in the case of any polynomial. Well, I believe no one needs to prove this. It just follows from the definition. The only thing I just want to clarify, the place where we use the fact that we deal with a field. So if the leading coefficient of f is an and the leading coefficient of g is bm, so here are the terms of the smaller degree, then f times g equals an times bm x to the n plus m plus the smaller coefficients. And since f capital is a field, the product of non-zero numbers is non-zero. So if these guys are non-zero, then it implies that the product is also non-zero. So this is the place where we use that f capital is a field. And actually, this proves the result in case of non-zero polynomials. And the case of zero polynomial is considered separately and simple. Okay. So now, why do, just in case, are there any questions? Okay. I believe that everything here is well known, and you're probably familiar with that. So now, the reason why we like polynomials in one variable, we have the Euclidean algorithm here. So, I don't know, is there anyone who doesn't know how to divide polynomials with remainder? Okay, that's cool. So let me just recall the formal definition. So if you have two polynomials, f and g, from here, and I will always assume that the coefficients live in a field, so f will always be a field, so I just don't want to mention this. And suppose that g is not equal to 0, then we can represent f in this form, where q and r are also polynomials, and the degree of r is strictly smaller than the degree of g. So let me underline these things like that. So in this case, we say that r is the remainder and q is the quotient. So, and how to determine here what is the divisor? Well, the divisor is the one present in this part of the condition. So if the degree of r is strictly smaller than the degree of g, then we divided f by g. And if the degree of r is strictly smaller than the degree of q, then we consider this as a division of f by q. Well, if both assumptions hold, then you may think that this is a division with a remainder with respect to q or with respect to g, doesn't matter. But the important part is what appears here is the divisor. Okay, now we will say that a polynomial g divides a polynomial f if f is present in the form g times h, where h is some polynomial from here. From this definition, it follows that the zero polynomial is divisible by everything. So just in case, so zero polynomial is divisible by everything. Okay, and there is a notion of the greatest common divisor of two polynomials. So if we have two polynomials, f and g, then we will say that a polynomial d is a greatest common divisor if the following two properties are satisfied. The first one says that d must be a divisor, so d divides f and d divides g. And the second property, well, this must be a greatest common divisor in the sense that if something else divides f and g, then it divides d. So if h divides f and h divides g, then h divides d. So in this sense, d is called a common greatest divisor. There are a lot of common greatest divisors, but the difference between them is insignificant, almost. So now, what do we know about common greatest divisors? So if, again, f and g are two polynomials, f is also a field, then first, the greatest common, there is always a greatest common divisor for any pair of polynomials. There exists a greatest common divisor for the polynomials f and g. That's the first claim. The second claim says that if there are two greatest common divisors, so if d1 and d2 are greatest common divisors, then there exists an invertible constant such that d1 equals c d2. And the third thing, there exists a pair of polynomials u and v such that the greatest common divisor, a greatest common divisor, is represented as a linear combination of the initial polynomials with these u and v as the coefficients. So this is the claim. So again, we have a pair of polynomials, no restrictions. Any of them could be 0. Two of them could be 0. It doesn't matter. then you can always find the greatest common divisor. Any different greatest common divisors are different by an invertible constant, and you can always represent a greatest common divisor in this form. Just in case, did you prove this during the discrete math course?
Not really. I guess we only proved the Euclidean algorithm only in case of.
I'm sorry, could you repeat? The sound here was too quiet. Could you repeat, please?
I suppose Andrew said that we haven't really touched on this.
So you didn't prove this?
Yes.
Okay. So, okay, just in case, the proof here actually is exactly the same as the proof in case of the integer numbers. And you use the Euclidean division algorithm. So in exactly the same manner as you do it for the integers. So, I would like to skip actually the proof because if you just, well, let me say at least a couple of words about the proof. So the proof is exactly the same as in case of the integer numbers. So if you just take the proof for the integer numbers and replace every word integer by the word polynomial, you will get the required proof. The only problem in case of integers, you use the notion of the module of the integer. So here you can replace the notion of the module by this expression. You just raise e to the power of the degree of f. And this formula actually explains why you want the degree of the zero polynomial to be minus infinity, because in this case, the module of the zero polynomial is exactly 0. Well, using this notation, you just repeat the proof for integers, and you will get exactly the same result for the polynomials. So probably it's not worth doing it here. Well, and the main trick is this. How do you use the Euclidean algorithm? Well, there is an effective way of finding a greatest common divisor. So it's based on the Euclidean algorithm, and we will discuss this algorithm during the seminar session. So how to find a greatest common divisor and represent it in this form. So additionally, we want to find this u and v, and actually, first of all, we need to prove this, and then you can prove all other properties without any problems.
And what is d in this formula? One of the the only greatest common divisor?
Yeah, I should say, suppose that, let me say it like that, suppose d is the greatest common divisor for f and g, then there exists u and v such that this equality holds.
And how is it possible that there are two greatest common divisors?
How it's possible that there are two greatest common divisors? Okay, let me show you the example. It's actually simple. It's like in the case of integers, a greatest common divisor, if d is the greatest common divisor, then minus d is also a greatest common divisor. So exactly the same thing happens here. So for example, if you take a polynomial like x squared plus x and x squared, so this is an example. So a greatest common divisor of these guys is equal to x. But what was our field? Our field, let's say we deal with Rx. We deal with polynomials with the real coefficients, but then you can multiply this polynomial by any invertible integer. For example, 2x, 1 over the 3x, like a square root of pi over 2x. All of these things are greatest common divisors of these two polynomials. Because if x divides this and this guy, then 2x also divides both of these guys. And this thing divides this, and this thing divides this.
But
there is no.
What's the definition of the word divides then?
Oh, the word divides means that this polynomial is presented as a product of this polynomial and some other polynomial. So for example, x squared equals square root of pi over 2x times 2 over square root of pi x. So we presented this polynomial, this one, as a product of two polynomials, this and this. So yeah, so this is the reason why the greatest common divisor is not uniquely determined, because you can multiply by an invertible constant. So everything here is uniquely determined if the leading coefficient is 1. So if we say, well, if we put this additional condition here, that is the leading coefficients to be 1, then the greatest common divisor is uniquely determined. But I hope now it's clear. Okay. Yeah, and just in case, I want to clarify several specific cases. In example number 2, so what if both polynomials are 0? So what is the greatest common divisor of 0 and 0? Well, by definition, it's 0. Why? Well, first of all, by definition, 0 is divisible by any polynomial, because 0 equals, say, h times 0. So h divides 0 for any polynomial, h. So every polynomial divides 0, but now we want to find greatest polynomial, the greatest divisor, which means that we want to find a divisor which is divisible by any other divisor. So the same equality explains that 0 is the greatest divisor. So it's divisible by any other divisor, by any other polynomial, and any other polynomial is a divisor. So this also explains this. So in this partial case, the greatest common divisor of two zero polynomials is just 0. Another example is when one of the polynomials is not 0 and the other one is 0. In this case, the greatest common divisor of f and 0 is just f. Because in this case, f divides 0, and if one of them divides the other one, then the greatest common divisor is, by definition, the one which divides the other one. So this is just by definition. So in this particular case, it's very easy to compute the greatest common divisor. You just take the non-zero one. Okay. So how do you compute the greatest common divisor in general? So there is the Euclidean algorithm. So we need one simple remark. If we have two polynomials, f and g, then the greatest common divisor of, and say we have another polynomial h, then the greatest common divisor of f and g is exactly the same as the greatest common divisor of f and g minus h times f. So first of all, I want to explain why this is true, and second, I want to explain the algorithm based on this equality. So first, why this is true? Well, in order to show that the greatest common divisor for these guys is the same as the greatest common divisor for these guys. Well, by the way, what do I mean by the greatest common divisor if it's not unique? You may think that the left-hand side and the right-hand side is the set of greatest common divisors and both sets are the same, or you may think of the left-hand side as the greatest common divisor with the leading coefficient being 1, and the same for the right-hand side. This is the greatest common divisor of these two polynomials with the leading coefficient being 1. In this case, these two polynomials are the same. Well, how do you prove this? In this case, so let me show you how to do that. So let's consider the both pairs. Now, first of all, suppose that some polynomial h divides f and g. Then it's clear that h divides f. But now, if h divides f and h divides g, then it's clear that h divides this difference, just by definition, because this is representable as h times something, and this is representable as h times something, then the whole expression is representable as h times something. Then it means that h also divides the second polynomial. And vice versa. If you denote this polynomial as g prime, then g equals g prime plus hf. So if h divides f and g prime, then by this exactly the same argument, there is the same h. I'm sorry, I just noticed that I used the same notation in two different situations. Let's denote by say, I don't know, h prime. Let it be h prime. I'm sorry. So these h and these h are different polynomials. I'm sorry for the collision of the notation. So again, in this case, we had if h prime divides f and g, then h prime divides f and this expression. And if we denote this expression by g prime, then g is equal to this expression. And by the same argument, if h prime divides f and g prime, then h prime divides f and the same expression. So we have that the set of all common divisors, so the set of divisors for f and g is exactly the same as the set of divisors for f and g minus hf. But then how do we define the greatest common divisor? A greatest common divisor is an element here which is divisible by everything else. And a greatest common divisor for these polynomials is a polynomial here which is divisible by everything else here. But since these two sets are the same, then the elements here and here divisible by anything else are exactly the same. So from this equality, it follows that the greatest common divisor for f and g are the same as the greatest common divisors for these two polynomials. And we're done. So this immediately follows from the abstract definition. Now, how do we compute a greatest common divisor using this observation? So first of all, if we're given two polynomials, we can do this. We can divide f with a remainder by g. Then, as you can see, well, let's say that this thing denotes the greatest common divisor with the leading coefficient being 1. Using the previous rule, we see that the greatest common divisor of this thing is equal to the greatest common divisor. The greatest common divisor of this thing is equal to the greatest common divisor of this thing. Formally I use a slightly different rule here because I switched the polynomial f by the polynomial g here, but the proof for this equality is exactly the same as I did before. So using this, we see that this polynomial is exactly the remainder R1. But what do we know about the remainder? The degree of the remainder is strictly smaller than the degree of the polynomial G. So now we can repeat the same algorithm, but we replace f by the polynomial G, and we replace G by the remainder R1, and we divide G by R1 with the remainder, and we will get some quotient Q2 and some new remainder R2. And again, by the same rule, the greatest common divisor for G and R1 is equal to the greatest common divisor of R1 and R2, and also the degree of R2 is strictly smaller than the degree of R1. And we can repeat the process, and the process cannot go infinitely many times, because at each step we decrease the degree of the remainder. So at some point the remainder must be 0. So at some point we will get that, say, R k minus 1 equals Q k R k plus the notation here, k plus 1 plus rk plus 1, and this guy will be 0 at some point. And in this situation, the remainder on the previous step, rk, is the greatest common divisor. Why? Because here we will get this long sequence of equalities, and at the end we will get this, and this guy is 0, and by the previous case, if one of the polynomials is 0, then the greatest common divisor is equal to the other one. So this is the algorithm for computation of the greatest common divisor using the Euclidean algorithm. So you just divide all these guys and you shift the one we shift it like this. F is replaced by the divisor, and the divisor G is replaced by the remainder. And at each step we repeat this procedure. Okay, are there any questions regarding this algorithm? Okay, so the algorithm is exactly the same as the one for the integer numbers. So it's probably a very familiar one. So now I want to describe ideals in the polynomial ring. So suppose, let me formulate a claim. Suppose, so F is a field. Let me specify here. And suppose I is an ideal in the polynomial ring. Ideal. Then there exists a polynomial f such that I is equal to the set of all polynomials divisible by f. So in case of integers, we denoted this set like f times the whole ring, so we can denote it by f times f of x. And actually this set has the special notation, which is f in round brackets, f in parentheses. So again, the claim is that every ideal in the polynomial ring is of this form. It's actually called the principal ideal, but the term doesn't matter here, but just in case. And how do you prove this? Well, you consider two cases. well, if you remember the proof for the integers, you'll probably understand how to prove this. So there are two cases. Either there is only a zero element, or there is a non-zero polynomial in the ideal. So in this case, in the first case, we take I to be 0 times f of x. So here f is 0. So it's clear. In the second case, we define h to be a polynomial of I, which is non-zero, and the degree of h is the smallest possible. So we take a polynomial of I with the smallest possible degree. And then we just need to show that every other polynomial is divisible by h. So if we take an arbitrary g of I, we divide g by h with the remainder, and here we have that the degree of the remainder is strictly smaller than the degree of the polynomial h, the one we used here. But you can represent R in the form G minus QH, and the element G was an element of the ideal I. H, by definition, was an element of the ideal I. By the definition of the ideal, if H is in the ideal, then the product of QH is also in the ideal. So this implies that the whole expression is in the ideal I. So R is also a polynomial from the ideal I. It has smaller degree than the polynomial H, but H was a polynomial in the ideal, was a non-zero polynomial in the ideal I with the smallest possible degree. So if R has smaller degree and is also inside the ideal, the only option here is that R must be 0. So just by definition of H, we have that R must be 0, but the later means that G is equal Q times H, which means that H divides every polynomial G in the ideal I. So in this case, I is equal to H times f of x. So the proof is exactly the same. Okay, are there any questions regarding the proof? Well, hopefully it should be clear, because we already did this in case of integers, in case of reminders, and we will repeat the same thing in one case. So you will see the same proof again and again. So probably it's for good. So now I want to discuss one important property of polynomial ring in one variable. So the unique factorization domain, UFD, unique factorization domain. So what does it mean? So first of all, I want to give several definitions. So suppose F is a field. So then we need some analogy of a prime number. So in case of integer numbers, we have prime numbers, and all other numbers are presented uniquely as a product of prime numbers. So here we want to develop the same theory. So, but first of all, we need an analogy for the prime number. So we say that a polynomial f is reducible. This is not an analogy for the prime number. So we say that f is reducible if there exist polynomials g and h from f of x such that f is a product of g and h, and also the degree of g is between 0 and the degree of f, and also the degree of h is between 0 and the degree of f. So what does it mean? It means that if you have, say, x times x plus 1 equals x squared plus x, so this is your f, this is your g, and this is your h. So in this case, you can represent f as the product of polynomials of strictly smaller degree than the degree of the polynomial f. Well, this inequality simply means that neither g nor h is a constant. So both of them must be polynomials. So in this case, we say that f is reducible, and this simply means that you can factorize f as a product of two other non-constant polynomials. Well, as you may guess, we will call the polynomial f irreducible in the contrary case. But let me specify or pronounce exactly what it means here. Irreducible if for every polynomial g and h from f of x, if f equals g times h, then either g is constant or h is constant. And just in case, if you didn't notice, in both cases for reducible and irreducible polynomials, I consider polynomials of degree strictly greater than 0. I consider non-constant polynomials. So it doesn't make sense to discuss reducibility and irreducibility for constant polynomials. So in this context, all polynomials are non-constant. So they have positive degree. And yeah, just in case, I will say that f is monic if its leading coefficient is 1. If the leading coefficient is 1. Okay, now we're ready to formulate the unique factorization property for the polynomial rings. The claim, oh, by the way, let me give you a couple of examples. So, for example, if you take this ring C of x, where C is the field of complex numbers, then only linear polynomials are irreducible. These are irreducible, and all polynomials of degree strictly larger than 1 are reducible. This is because over complex numbers, you can factorize every polynomial as the product of linear ones. In case of real numbers, well, for example, well, of course, all the linear polynomials are irreducible. But also, some polynomials of square 2 are irreducible. So a polynomial of this form is irreducible, well, if and only if it doesn't have a root, but explicitly this means that the expression a squared minus b minus 4b is strictly negative. So in this case, this polynomial is also irreducible. And these are all irreducible polynomials over this in this ring. Well, in case of rational numbers, the situation is more interesting. Well, it's hard to describe all irreducible polynomials, but let me give you an example. Well, an interesting example is this one, x squared minus 5. Well, it's reducible as a polynomial with real coefficients, but it's irreducible as a polynomial with rational coefficients. So this is an example of irreducible polynomial. And actually, in case of the rational field, for every degree, we can find an irreducible polynomial of that degree. Well, for example, x to the n minus 5 is irreducible for any n. I'm not going to prove this, but just in case, I just want you to know the examples and the fact that for rational numbers, for any possible degree, you can find an irreducible polynomial, and this is an explicit example. Okay, so and now we're ready to formulate the UFD property claim. UFD. UFD means unique factorization domain. I don't want to explain what exactly this means, but let's use the term as it is, as a magical spell which names the claim I'm going to present. So suppose F is a field. Then every polynomial, every non-constant polynomial, yes, the Russian translation is область целостности, exactly. In Russian it's called область с однозначным разложением на множители. But I just don't want to explain what the term domain means and so on and so on. It's simple. I just want to formulate a claim about polynomials. So it's just better to formulate precisely what I mean. So then every polynomial is uniquely presented, uniquely presented in the form f equals a times p1 to the k1 and so on, pr to the kr, where a is a non-zero constant, p1, pr are distinct monic irreducible polynomials, different monic irreducible polynomials, and k1, kr are positive integers. So every polynomial is uniquely presented in this form. So this is a generalization of the same claim for integers. You know that each integer number can be presented as this product. In case of integers, here we use plus minus 1, so that's the only option for an invertible integer. And here, instead of irreducible monic polynomials, we use prime numbers, and here we use powers of prime numbers, which are just positive integers. So this is exactly the same claim. I'm not going to prove this. It's a terrible formal proof. The proof doesn't teach us anything. I mean, you will know how to prove this claim, but it will be useless for you. It's much better to understand how to use this claim and actually to know that this fact holds. Okay, but I still want to prove one specific case of this claim. So in order to demonstrate the technique, how do we use greatest common divisors and its properties. So claim, suppose that F is a field as usual, and suppose we're given two polynomials f and g. Oh, you know what? Okay, let me show you. We have two polynomials f and g, and yeah, three polynomials f, g, and h. Okay, and suppose that f and g are co-prime, which means that their greatest common divisor is 1, and both of them divide h. F divides h, and g divides h. Okay, then the product fg divides h. So this is the partial case of the previous claim. Actually, this result is used to prove the previous one. So this is exactly the same what happens in case of integers. If you have two coprime integers and your number is divisible by each of them, then it's divisible by the product. So how do we prove this? So first of all, we use the fact that the greatest common divisor is presented in this form where u and v are some polynomials. But then you just multiply this equality by h and you will get this expression. But now you know that h is divisible by g, so the whole product here is divisible by gf. Here you know that h is divisible by f, so the whole product here is divisible by gf. So now we see that the sum is divisible by gf, and that's it. And this is a very common trick how to use this expansion of the greatest common divisor into a sum of the initial polynomials with the coefficients being also polynomials for proving a fact like this. So if you want to prove something like this, like this claim, you usually use this expansion of the greatest common divisor into the sum. Okay, now we're ready to discuss the main object of today's lecture, which is the ring of the reminders. So the ring of the reminders. Well, you see, the ring of integers and the ring of polynomials in one variable, they are very similar because of the existence of the division algorithm, the Euclidean algorithm. So this enables us to define exactly the same ring as we did in case of integers, which is the ring of reminders. So suppose that f is a field. And we fix a polynomial f from the ring of polynomials. Now I want to define a ring which will be denoted by this strange notation. It's called the ring of the reminders modular f, or the quotient ring with respect to f. So there are two different names, the ring of reminders with respect to f, or the quotient ring by f. Okay, in order to define a ring, I have to specify three pieces of data. The first thing, a set. The second thing, an addition on this set. The third thing is multiplication on this set. And then I have to check that all these operations obey the required axioms. So I'm going to present you the data, but I'm going to skip the proof that the data satisfy all the required axioms, but the lecture notes will contain the required proof. So there is one special case. If f is 0, then we will define this to be just the ring of usual polynomials. And now I want to define this ring of reminders in case of a non-zero polynomial f. In this, so as a set of f of x, motion f, is that the set of all polynomials of degree strictly smaller than degree of f. So this is our set. So if f has degree n, then here we have a0 plus a1x plus and so on, plus n minus 1x to the power of n minus 1 if n is equal to the degree of f. So this is how this set looks like. Now I want to define the operations. First of all, the addition. Well, if we have two polynomials like this, for example, g1 and g2 is another polynomial b0 plus plus b1x plus and so on plus bn minus 1x n minus 1. Here the degrees are bounded by the same boundary, which is the degree of the polynomial f. So g1 plus g2 is also, well, here the plus means the usual addition of the polynomials. And if you add two polynomials from this set, the sum is also inside the set, so it's a well-defined operation. So this will be our addition. So what about multiplication? Well, if you multiply g1 by g2, well, the result will be a polynomial of a degree larger than the degree, or probably equal to the degree of f. So in order to compute the result, we take the result modular the polynomial f. So we take the remainder of this thing with respect to f. So let's say g1 times g2 equals q f plus r, where the degree of r is strictly smaller than the degree of f. Then the product is just defined to be r, the remainder of the product. And the remainder, it depends on the polynomial f because we divide the product by the polynomial f. So if we choose a different polynomial f, the remainder will be different. So the product depends on the choice of this polynomial. So the addition doesn't depend on the choice of the polynomial, but the product depends. So the claim without proof, well, the proof will be in the lecture notes. The claim that the set f of x modulo f or quotient f with the addition and the operation defined above is a commutative ring. Okay, so what do we want to know about this ring? First of all, several remarks. Well, as we can see, this set is a subset in the set of all polynomials. Moreover, this, if we consider just addition, so if I add addition here, let me write it on the left-hand side and on the right-hand side here, then this is a subgroup. So with respect to addition only. But if we add multiplication, well, this inclusion does not preserve multiplication. So multiplication is not preserved. Which means that if you multiply two elements here and two elements here, the result will be different. Well, and it's clear from this formula. So if you multiply elements here, the result is r, but if you multiply the same polynomials here, the result is just g1 times g2. So that's why this embedding is not an embedding of rings. So this is not a subring here. So important thing that f of x quotient by f is not, I'm sorry, a subring of f of x. This is very important. well, you may consider it as a subset, but it's not a subring. The second remark is this. On the other hand, you can produce a homomorphism in the opposite direction. If you take an arbitrary polynomial, you can take it to G modular F. So this is the second remark. And this map is a surjective homomorphism of rings. So this map is a surjective homomorphism of rings. So you cannot embed this thing into this one, but you have a map in the opposite direction. So you can take any polynomial and produce a the corresponding remainder in this ring. And this map, taking G to G modular F, is a homomorphism of rings, and it's obviously surjective. Okay, let me discuss one more thing.
And could you clarify, please, what is G modular F? What is some polynomial modular?
Oh, G modular F means the remainder of G with respect to F. So
okay.
yeah, you just divide, and this is G modular F. So you take the remainder.
Okay.
Okay, no problem. Yeah, I didn't say it explicitly, so thanks for the question. Okay. Well, let me formulate another claim. I hope I have enough time for doing that. Well, at least we can eat the break between lecture and the seminar. So I guess I'll do that. So now I want to at least, okay, let me formulate another result. So another result is the Chinese remainder theorem for polynomials. So claim the Chinese remainder theorem. Remainder theorem. So suppose, so as usual, F is a field. Now, F and G are co-prime polynomials. Then, let me write the formula down, and then I will explain what's going on. F of x quotient by F times G goes to F of x quotient by F times F of x quotient by G. And the map works like this. You take H to the H modular F, H modular G. Let me show you the claim. So it's still not a claim, but the beginning of the claim is this. If you're given a field and you're given two polynomials, F and G, two co-prime polynomials from this ring, then the map from this ring of reminders to the product of these rings, given by these formulas, you just take a reminder here, and you take its reminder with respect to F, and the second coordinate is a reminder with respect to G. Then this map, as you may guess, is an isomorphism of rings. So this is the claim. So this is exactly the same claim as it was for the integers. And here we use Zn times m goes to Zn times Zm. So this is just the analogy of Zn times n. So are there any questions regarding the claim? Okay, I hope the statement is clear. So Let me show you the proof of the claim. First of all, what do we need to do in order to show that this is a homomorphic isomorphism? Well, the first thing we need to show that, let me denote this map by phi capital. So first of all, we need to show that phi capital is a homomorphism, which means it preserves the addition, multiplication, and it takes the identity with respect to multiplication to the identity with respect to multiplication, which means it takes the element 1 to the element 1. Well, it's a straightforward computation, actually, that addition and multiplication are preserved here. And I want to skip this. So the fact that phi preserves these things is a straightforward computation. Is a straightforward computation. So, and I think and actually the proof of this fact is exactly the same as it was in case of integer numbers. So I think it's not worth wasting our time for doing this again. Okay, the next thing we want to show that the map is injective. So phi is injective. Well, let's take an arbitrary polynomial h here, f of x quotient by fg. What does it mean? It means that h is a polynomial of degree strictly smaller than the product g fg, and it goes to the pair h modular f and h modular g. Now, in order to prove that a homomorphism of rings is injective, it is enough to show that the kernel of the homomorphism consists of the zero polynomial only. So this means that we should assume that h is a polynomial going to 0, and we need to prove that h itself is 0. So, but what does it mean that h goes to 0 here? It means that f divides h. What does it mean that h goes to 0 here? It means that g divides h. The remainder is 0. But now we know that f and g are coprime. So by the choice, by the hypothesis of the claim, f and g were coprime, and because of this, it follows that f times g divides h. But h was an element of this set. It was a polynomial of the degree strictly smaller than the degree of g times a, f times g. So the only option here is that h is 0, and this proved the injectivity. Are there any questions? Okay, so
What
now
is f of x divided by fg in parentheses? Could you
okay.
recall the definition?
So okay, let me recall it here below. So f of x quotient by f times g is the set of all polynomials h such that the degree of h is strictly smaller than the degree of f times g. So this is just by definition of the ring of reminders. I consider all reminders with respect to this polynomial. So this polynomial is just a product of polynomial f and g.
Okay.
So I just consider all possible reminders with respect to this polynomial, which means I consider all polynomials of degree strictly smaller than this polynomial. Okay?
Okay, thanks.
So, okay, now this explains why the map phi capital is injective. Now I want to show why it's surjective. And here I will use some linear algebra. So let's see that this guy is a vector space over F. And actually, it has a basis. For example, let's suppose that the degree of F is n, the degree of G is m, then the degree of F times G will be n plus m, and a basis of this space is 1, x to the power of 2, and so on, x to the power n plus m minus 1. So this will be a basis of the space. So this space has dimension n plus m. So the dimension of this guy over F is n plus m. In a similar way, f of x quotient f is a vector space over F, and its dimension is n, the degree of the polynomial f. And the dimension of this guy is m. And similarly, the dimension of this space, so this thing, is also a vector space, which is a direct sum of these two spaces. I don't know, are you familiar or not with this term, but
Yes, we are.
Yeah, okay.
We
so
touched on it.
if you replace the symbol of the Cartesian product by the symbol of the direct product, you will see that this space is exactly the direct product or the direct sum of this and this space. And the dimension of the direct sum is just the sum of dimensions. So the dimension of this space is n plus m as well. It's the sum of these two dimensions. Okay, but now what do we have? Let me show you. I just want to go back to the claim. We have that this guy is the space of the dimension n plus m. This guy is the space of the dimension n plus m. And phi is a linear map, which is injective. So we have an injective map between two spaces of the same dimension, but then it's automatically surjective by the corresponding claim from the linear algebra. So let me write it here. So, oops, come on. Phi is a map from this quotient to this quotient. So phi is linear and injective. And these two spaces have the same dimension. So we know that in this case, phi must be surjective. And that's it. So this is the Chinese reminder theorem for the ring of reminders in polynomial case. So are there any questions? So we're running out of time, so I will probably make several remarks, and that will be it. Okay, let me summarize what's going on here. So until now, we discussed the notion of this strange object, which is the ring of the reminders, or a quotient ring of the polynomial ring with respect to a polynomial. And this is a direct analogy of the remainder ring for integers. And this is the extension of the theorem of the Chinese remainder theorem for integers to the case of polynomials. And it's used in exactly the same manner as we did it in case of integers. So, and by the way, since we used integers in order to encode and decode some information, as you may guess, you can apply the similar ideas for these rings if the field f and the polynomial f small are appropriately chosen. Okay, so I want to add a couple of auxiliary remarks. So, well, let's discuss some properties of this ring of reminders. So, well, as before, f is a field. Suppose f is a polynomial. Well, let's say non-zero polynomial, because the remainder ring in case of the zero polynomial is just the f of x itself, so it's not interesting. So let's consider this guy. So let me say this as a claim. Well, this guy is a field if and only if f is irreducible. But this is the same claim as for the integers, where we know that the remainder ring for the integers is a field if and only if the number here is prime. So since irreducible polynomial is the direct analogy of a prime number, so this is the claim we expect to see here. So why this happens? Let me show you. So first of all, suppose that so we want to show that from left to right. So suppose that this guy is a field, then we want to show that f is irreducible. Suppose not. Suppose that f is the product of two polynomials and the degree of g is strictly smaller than the degree of f, and the degree of h is strictly smaller than the degree of f. In this case, g and h are non-zero elements of this ring, but g times h is equal to 0 just by definition here. So we have 0 divisors, but in this case, g and h as well is not invertible, because if it were invertible, we would multiply by g inverse and h must be 0 in this case, but h is not 0. So, but if it were a field, then every non-zero element would be invertible. So a contradiction, and the contradiction arose from our assumption that f was reducible. So this is how you prove this in one direction. And in the other direction, suppose that f is irreducible and g is a non-zero element of this ring. Then g and f must be coprime, and as we know, the greatest common divisor must be a linear combination of f and g, where u and v are some polynomials. But now we may consider this equality modular f. Let's take the remainder of the left and the right hand side. This gives us 1 equals u times g in f of x modular f. And this equality means that u is actually G inverse in this ring, which completes the proof, and that's it. Okay, I think that's it for the lecture. If you have any questions, please ask. If there are no questions, then the seminar for the group 191 will be in a couple of minutes here. So you may stay here with me.
I suppose there is a mistake with the basis. When you define the basis for polynomials, you said that the maximum degree is n plus m minus 1, but it should be n plus m. Because if n is equal to 0, m.
No, the degree starts from 0. 1
but
to the power.
Oh, well, I'm saying that if n is equal to 0 and m is equal to 0.
But here, well, if n equals, okay, if your polynomials are co-prime, then it's impossible them to have 0 degree. Well, here we assume that f and g, automatically we assume that f and g are not constant.
Makes sense, yeah, thank you.
Well, I can still extend the claim to the case of constant polynomials, but it's meaningless.
But why, if polynomials are coprime, then they are not constant?
Well, okay, I see what you're saying. Well, okay. You're right. I should explicitly state here that f and g are not constants. So I have to exclude elements of the field f. Thank you.
And there is, furthermore, there is a problem, since if we assume that it is a direct sum, that means that the intersection of these two vector subspaces is a 0 vector space, while it is not actually so.
Oh, but here, when I consider the direct product, well, it means like external direct sum. I take like a copy of this guy, a copy of this guy, and then produce a direct sum. I do not consider this sum inside the polynomial ring.
Okay, I see.
Okay. So I consider them as a subset of this Cartesian product. And inside this Cartesian product, this guy and this guy, they intersect each other by the 0 polynomial order. Are there any other questions? Okay, so I'll see you, well, just give me 1 minute. I will continue the seminar in a minute.